Hello and welcome to the following revision session for AQA A-Level Physics Paper 3 in the Astrophysics option of Cosmology. So in today's revision session, if we've been successful and we've learned today, we should be able to answer A-Level Physics exam style questions. Assess our understanding on A-Level Physics and then finally understand what topics we need to improve upon for A-Level Physics. So how should you prepare for this revision session? When completing your work in this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side. In this left hand side section, write down your working out and answers to the questions in the revision session. When you're doing this, make sure you write in full sentences to show your full working out. Whilst in the right hand side, write down any bits of information which you find useful or any hints and tips on answering questions from this revision session. After the end of the revision session, write up these notes into a revision sheet for you to use independently. Now, how should you be revising for AQA A-Level Physics? Firstly, learn the key facts. Use revision guides, class workbooks, student prep notes, and the textbooks to learn the key ideas of the course. Then test yourself. Use things like Caboodle, Seneca, knowledge checkers to quickly test your own knowledge. Finally, use exam preparation books, homework books, supervised study books, additional workbooks to answer exam questions and mark your own work. So you should learn the key facts, test yourself, and practice exam style questions. Now, what are the key facts regarding the cosmology topic in astrophysics? Well, the first thing to look at is the Doppler effect. So, a shift in the observed wavelength or frequency of light due to the relative motion between the source and the observer. So, it is change in F over F equals V over C, which equals this redshift factor Z, or change in lambda over lambda is equal to V over C, which is equal to Z. Now, we use the Doppler shift to detect and analyse binary star systems, especially when viewed in the plane of orbit. Now, for galaxies and quasars, the redshift of spectral lines indicates galaxies are moving away from us. The greater the redshift, the faster the recession. Now, Hubble's law is V equals hd, and it shows the idea the universe is expanding. This allows us to estimate the age of the universe assuming h is a constant, with the age being 1 over h. Now, the evidence for the Big Bang is the cosmic microwave background radiation, CMBR, with the uniform background radiation, which is a remnant of the early universe, and the relative abundance of hydrogen and helium. This matches the theoretical predictions from the primordial nucleosynthesis at the start of the universe. These support the Big Bang model of universal origin and evolution. Now, quasars are the most distant measurable objects in the universe. They're incredibly luminous and emit across many parts of the spectrum: radio, optical, and X-ray. Now, they were first identified as bright radio sources with unusual spectra. The optical observation showed large redshifts indicating high recession velocities and vast distances. Now, large redshifts allow for the calculation of their distance. Now, with this distance and the observed intensity, you may then be able to estimate their power output, which often exceeds entire galaxies. Now, they're believed to be powered by the accretion of matter onto a supermassive black hole at the centre of a young galaxy, and they're highly energetic due to the gravitational energy released in this process. Now, exoplanets are extremely difficult to detect directly, as they're very faint compared to their host stars. They're close to stars in angular terms, and most can't be resolved separately with telescopes. So there are two indirect methods for detecting exoplanets. The radial velocity method, which the planet causes its star to wobble slightly due to gravitational interaction. This wobble causes periodic red and blue shifts in the star spectrum. So this allows estimation of the orbital period and the minimum mass of the planet. Whilst the transit method is where a planet passes in front of its host star but harshly blocking out its light. This results in small periodic dips in brightness or an observable light curve. We can use this to determine the radius of the exoplanet, the orbital period, possible atmospheric information. Now, in a typical light curve, it's a graph of brightness against time, and it shows a sharp drop during the ingress, a flat bottom if the planet is fully in front of the star, and a rise during the egress. Now, the depth of the dip relates to the planet's size, and the duration gives clues about the orbital period of the planet. So let's have a look at some general check questions regarding cosmology. As stars moving away from the Earth, the wavelengths of spectral lines in the light received from the star are measured. These wavelengths are not the same as the wavelengths of the same lines measured from a source in the laboratory. What explains the difference? The light arrives at the Earth with a longer wavelength. The motion does not change the wavelength of emission, and the wavelength increases when the source is receding. Explain what redshift is. If a star or galaxy is moving away from us, the light it emits is stretched to longer wavelengths, making it appear redder. Explain what blue shift is. If a star or galaxy is moving towards us, the light it emits is compressed to shorter wavelengths, making it appear bluer. Absorption lines in the spectrum of a light from a star are shifted to higher frequencies than the same lines viewed from a source on Earth. What can be concluded from this? The star is moving towards the Earth as the lines are shifting towards higher frequencies and lower wavelengths. A star is moving away from the Earth at a speed of 3 times 10 to the 6 meters per second. Calculate the redshift Z observed in the light from this star. Z is equal to V over C, so 3 times 10 to the 6 over 3 times 10 to the 8, so it equals 0.01. A star is rotating with a velocity of 2 times 10 to the 4 meters per second at its equator. If the star's radius is 7 times 10 to the 8 meters, calculate the Doppler shift, the observed change in wavelength observed at the equator. Assume the original wavelength of the light is 500 nanometers. So we can say change in lambda over lambda is V over C. So change in lambda is therefore V times by lambda over C. We pop in all the values, which is V is going to be 2 times 10 to the 8. Okay, and then we can pop it all through, we get 3.3 times 10 to the minus 11 meters. A distant galaxy emits light at a rest wavelength of 500 nanometers. Due to its motion, we observe the light at 520 nanometers. Calculate the redshift. Determine the velocity of the galaxy relative to Earth. So we know Z is equal to change in lambda over lambda. Now we don't need to convert from nanometers into meters as it's a ratio. So it's 20 over 500, which is 0.04. So V is Z times by C. We pop in the values, you get 1.2 times 10 to the 7 meters per second. A binary star system consisting of 2 stars orbiting a common centre of mass. One star moves towards the Earth at 50 km per second while the other moves away at 50 km per second. Calculate the maximum observed wavelength shift for a spectral line of 600 nanometers. So we know change in lambda over lambda is equal to V over C. We therefore pop the values in and we can work out our value for change in lambda, which we get to be 0.10 nanometers. Now as one star is blue shifted, the other will be red shifted. This means the total observed wavelength shift is going to be 0.20 nanometers. The next question says, a star rotates with a maximum surface speed of 30 kilometers per second. If we observe a spectral line at 650 nanometers, calculate the wavelength difference, the change in lambda, between the approaching and receding edges. So, pause the video now, and then unpause the video when you want to go through your answer. So we know change in lambda over lambda is equal to V over C. We can then pop all the values in and work out change in lambda. So we get 0.065 nanometers. As one edge is blue shifted and the other is red shifted, that means our total observed wavelength shift is going to be double that value, so it's 0.13 nanometers. What is the significance of Hubble's law to cosmology? Hubble's law is significant because it provides evidence for the expansion of the universe. It implies that galaxies are moving away from each other, suggesting that the universe is expanding. The observation supports the Big Bang model of the origin of the universe. Explain how Hubble's law provides a simple interpretation of the expansion of the universe. Hubble's law indicates that galaxies are moving away from each other, with their recession velocities proportional to their distances. This suggests that the universe is expanding uniformly. The further away a galaxy is, the faster it appears to be receding. This observation supports the idea that the universe began from a single point, the Big Bang model, and has been expanding ever since. A galaxy is 150 megaparsecs away from the Earth. If Hubble's constant is 70 km per second per megaparsec, calculate the galaxy's recession velocity. We know V is equal to hd, so 70 times by 150 is 10,500 km per second. A galaxy is observed to have a redshift corresponding to a recession velocity of 2 times 10 to the 6 meters per second. If Hubble's constant is 70 km per second per megaparsec, calculate the distance to the galaxy. Well, d is v over h, so it's 2 times 10 to the 3 over 70, which is 28.57 megaparsecs. An astronomer observes a galaxy moving away at 25,000 km per second. If Hubble's constant is 70 km per second per megaparsec, calculate the distance to the galaxy. We know d is v over h, so 25,000 over 70 is 357 megaparsecs. A galaxy is observed to have a redshift of 0.1. Calculate recession velocity and the distance from the Earth, assuming the Hubble constant is 70 km per second per megaparsec. We know v is equal to zc, so therefore v is 3 times 10 to the 7 meters per second, which is 3 times 10 to the 4 kilometers per second. So therefore d is equal to v over h, so it's 3 times 10 to the 4 over 70, which is 428.57 megaparsecs. State the Big Bang in simple terms. The Big Bang states that the universe originated from a single, extremely hot and dense point around 13.8 billion years ago and has been expanding ever since. What is the cosmic microwave background radiation? The CMBR is a low-energy radiation that fills the entire universe and is detected as microwaves. It's the afterglow of the Big Bang, left over when the universe first became transparent 380,000 years after the Big Bang. How does the CMBR support the Big Bang theory? The Big Bang model predicts that after the early universe cooled, it would leave behind residual radiation. The radiation was first detected in 1965 by Penzias and Wilson and has been a temperature of 2.73 Kelvin, matching predictions. The CMBR is uniform in all directions, but small fluctuations in it explain galaxy formation. What is the relative abundance of hydrogen and helium in the universe? There is 75% hydrogen and 25% helium of normal matter. How does this support the Big Bang theory? The Big Bang nucleosynthesis model predicts that the hydrogen-helium formed in the first few minutes after the Big Bang. The observed helium abundance matches the predictions from nuclear fusion calculations. Stars can't produce enough helium to explain this abundance, meaning it must have formed in the early universe. How can we determine that quasars are the most powerful objects in the universe? When observing their redshift, we can determine that they must be a great distance away from us, and they must have a highly observable apparent magnitude. This indicates they have a high absolute magnitude. How can we determine that quasars are objects which existed in the distant past? The only quasars that are observed are found to be far away. This means that electromagnetic radiation must have left a long time ago to reach us, so they must have existed in the distant past. Why does a quasar emit radiation? A quasar is produced by a supermassive black hole. As matter accelerates into the black hole, the charged particles in the matter release radiation. Why does a quasar emit gamma radiation predominantly, but is observed on Earth as a bright radio source? The gamma radiation is redshifted as it travels through the voids of the universe. This causes the gamma radiation to be changed into radio waves via the Doppler effect. What is the difference between a quasar and an active galactic nuclei? A quasar is a type of active galactic nuclei. It's a name given to a powerful AGN that was found in the deep past of the universe. How were quasars originally discovered? In the 1950s and 60s, astronomers detected strong radio sources in the sky. When optical telescopes were pointed at these sources, they appeared as star-like points with very unusual spectral lines. What did astronomers find unusual about the spectra of a quasar? The spectral lines did not match any known stars. When corrected for redshift, the lines matched hydrogen emission lines, suggesting that the objects were very far away. The large redshifts implied a very high recession velocity and therefore great distances. A quasar has a redshift of 2. Explain what this tells us about the motion and distance of the quasar. This indicates the quasar is moving away very quickly and is very far away from when the universe was much younger. A quasar has a redshift of 2. Estimated recession velocity in distance, assuming h0, Hubble's constant, is 70 km per megaparsecs. We know v is equal to zc, so we can say 2 times 3 times 10 to the 8, 6 times 10 to the 8 meters per second. That's 6 times 10 to the 5 kilometers per second. We divide that by the Hubble constant, we get 8,571 megaparsecs. Describe how a quasar forms from a supermassive black hole in a young galaxy. A quasar forms when a supermassive black hole at a galaxy's centre becomes active by accreting large amounts of gas. In the early universe, galaxies contained much more gas and dust, which fueled the central black holes. The infalling matter formed an accretion disk, emitting intense radiation across the spectra. Would you be able to directly detect Mercury orbiting the Sun if you were located out the solar system? What is the most likely reason for this? Mercury would not be able to be detected, as the radiation emitted from the Sun would drown out the reflected radiation from Mercury. Would you be able to directly detect an exoplanet orbiting a dim red star? What is the most likely reason for this? You would not be able to directly detect the exoplanet, as the planet would subtend an angle smaller than the resolution of the telescope we currently use. What properties of an exoplanet can be detected via the radial velocity method? From this method, you can determine the mass, orbital velocity, and orbital period of a planet from the radial velocity method. Why can the radial velocity method not be used with many stars to detect exoplanets? For the radial velocity method, it can only be used if the Earth is in line with the line of sight of the star. If the Earth is perpendicular to the line of sight to the star, nothing will be detected. Why can the radial velocity method not be used to detect Earth-like exoplanets? For the radial velocity method, the mass of the exoplanet must be much larger than the Earth to detect a noticeable wobble on the star to produce a redshift-blue shift that can be measured. Using the transit method, how can the size of the exoplanet be determined? For the transit method, the size of the exoplanet can be determined by the size of the apparent magnitude dip in the star's light curve. Using the transit method, how can the orbital radius of the exoplanet be determined? For the transit method, the orbital radius of an exoplanet can be determined by the length of the apparent magnitude dip in the star's light curve. Why can it take a long time for the transit method to confirm the existence of an exoplanet which orbits at a great distance from its star? For the transit method, a periodic dip in the light curve needs to be established. This would take a long time if the orbital time period is long. Why might the transit method give false results for an exoplanet? For the transit method, a dip in the light curve might occur due to other astronomical objects passing in front of the star from the view of the Earth. Why can the transit method not be used with many stars to detect exoplanets? For the transit method, the Earth must be in the direct line of sight as the star. State 2 reasons why it's difficult to observe exoplanets directly. Firstly, brightness contrast. Stars are millions to billions of times brighter than their planets. And secondly, the distance in size. Exoplanets are very far away and appear very close to their host stars from Earth, making them hard to resolve. A Jupiter-sized planet is orbiting a distant star. Which detection method is more likely to detect this planet and why? A Jupiter-sized planet would cause a deep transit dip, making it easy to detect via the transit method. It would also cause a large radial velocity wobble, but only if the system is favourably aligned, so the transit method is much more likely to detect a large planet due to the deep dip in brightness. Let's now have a look at some questions regarding cosmology. An astronomer observes two binary star systems. System A lies exactly in the plane of its orbital motion relative to Earth. System B is orientated perpendicular to the plane of observation. The orbital plane faces the Earth directly. Using a high-resolution spectrometer, the astronomers detect a periodic shift in the absorption lines from System A, oscillating between redshift and blue shift, corresponding to a maximum or observed radial velocity of 65 km per second. Separately, light from a quasar shows an absorption line that in the lab appears at 486.1 nanometers, but is detected at 647.9 nanometers. Explain why System A shows a Doppler shift and System B does not. In your answer, refer to the components of the velocities involved. Calculate the maximum fractional change in wavelength observed in System A due to the Doppler effect. Determine the redshift for the quasar, then calculate the recession velocity. Then discuss how Doppler shifts can be used to distinguish between orbital motions in nearby systems like stars, and the cosmic expansion observed in quasars and galaxies. In your answer, evaluate the physical meaning of redshift in each case. So pause the video now, and then unpause the video when you want to go through your answer. In our first one, Doppler shifts occur due to the relative motion along the line of sight. System A has the orbital plane edge on, so stars have components of velocity towards and away from the Earth, causing red and blue shifts. System B, the orbital motion is perpendicular to the line of sight, so no Doppler shift is observed. We know change in lambda over lambda is equal to V over C, so the maximum fractional change is going to be V over C, so it's 2.17 times 10 to the minus 4. We know that Z is going to be the change in wavelength over the wavelength because it also will equal the change in lambda over lambda. So from the values given, we can work it through to be 0.333. We know V is equal to ZC, so we can work that through to be 1 times 10 to the 8 meters per second. Now, Doppler shifts in binary stars are due to orbital motion, their short period, and the symmetrical red and blue oscillations. The redshift from galaxies and quasars arises from the expansion of space, not local motion. So quasars show very large redshifts, often exceeding what orbital motion could possibly explain. Doppler shifts simply apply relative motion through space. Cosmological redshifts reflect the stretching of space itself. In binary star systems, redshifts vary periodically, allowing mass estimation in orbital period via mechanics. In quasars, the redshift helps measure distance and age of light, contributing to large-scale structure mapping and cosmology. Astronomer B analyses the radial velocity curve of a binary star system using spectral line data. The stars labelled A and B orbit their common centres of mass in circular orbits. The orbital plane is edge on to the observer, and the period of the system is determined to be 24 days. Measurements show that star A exhibits a maximum radial velocity of 40 km per second. Star B exhibits a maximum radial velocity of 20 km per second. Explain why the two stars have different radial velocities and what this indicates about their respective masses. Calculate the ratio of masses of the two stars. Assuming the separation between the two stars is 1 times 10 to the 11 meters, calculate the mass of each star. Then evaluate the reliability of the radial velocity data to determine the full dynamics of the binary star system. In your answer, consider both strengths and limitations of the method. So pause the video now, then unpause the video when you want to go through your answer. Right, the radial velocity differs because the stars orbit a common centre of mass conserving momentum. Star A's greater velocity implies it's less massive than star B. The product of the mass and velocity is constant for both stars, so it's an inversely proportional relationship. We know MAVA equals MBVB, so therefore MB over MA is VA over BB, so therefore it's 40 over 20, which is 0.5, so the ratio is 1 to 2. Now the total separation is 1 times 10 to the 11, so the total orbital speed is going to be VA plus VB, which is equal to 60 times 10 to the 3 meters per second. Our time period is 24 times 24 times 3,600, so it's 2.1 times 10 to the 6 seconds. The total mass can be worked out by using our equation of V equals 2 pi r over t, so m is therefore equal to v squared r over g. We pop in all the values, and therefore we can work it through, and we get mb to be 1.6 times 10 to 30 kilograms. And we worked the previous question, mass A is half of that, so it's 80 times 10 to 29 kilograms, and those values are consistent with sun-like stars. Now, the radial velocity method provides direct measurable evidence of orbital speeds. It's useful for estimating mass ratios and inferring orbital parameters. It does rely on the system being edge-on, as inclination affects observed velocities. We can't independently determine actual orbital radii without different assumptions or different data, so therefore it's useful but limited without geometry and distance data, so you've got to combine with other things, such as light curves. An astronomy team studies a newly discovered binary star system named AX12, where two stars orbit around a common centre of mass. The binary system is too distant to be resolved visually, but spectral analysis reveals periodic Doppler shifts in the star's absorption lines. The following observations are recorded. Star X shows spectral lines shifting with a maximum radial velocity of 120 km per second. Star Y shows spectral lines shifting with a maximum radial velocity of 40 km per second. The orbital period of the binary system is determined to be 15 days. Explain why Doppler shifts observed from the stars in spectropic binaries allow astronomers to determine orbital velocities even when the stars cannot be resolved visually. Calculate the ratio of the orbital radii of the two stars around the common centre of mass. Using the provided data to calculate the total mass of the AX12 binary system. Give your answers in solar masses and use the relationship given in the question. Evaluate the reliability and limitations of determined binary star parameters from Doppler shift measurements alone. In your answer, discuss potential uncertainties and suggest ways astronomers might overcome these limitations. So pause the video now, then unpause the video when you want to go through your answer. Right, Doppler shifts occur due to the star's relative motion along the observer's line of sight. The periodic shift from red to blue indicates that stars moving towards away from us respectively. Measuring the frequency of wavelength shift allows calculations from the orbital velocity of each star directly from the spectra. We know Rx over Ry is equal to Vx over Vy from ratios, so it's 120 over 40, so it equals 3. We can pop in the equations. Now remember, Vx plus Vy is 120 plus 40 times 10 to the 3, so it's 160,000 meters per second. The time period is going to be 1.3 times 10 to the 6 seconds. We can then pop in all the values given in the equation, and we work it through to be 1.27 times 10 to 31 kilograms. We then divide by the solar mass given on the equation sheet to get 6.35 solar masses. Now, the Doppler shift method directly measures orbital velocities, offering clear evidence of binary motion. It enables an accurate determination of mass ratios even when the stars cannot be resolved visually. It assumes the system is exactly edge-on, any inclination reduces measured velocities and thus introduces uncertainties. The circular orbit simplifies calculations, but real orbits could actually be elliptical. Now, improved reliability by combining Doppler shifts with other observational methods such as astronomy or Eclipse binaries can overcome these uncertainties. An observation team measures the redshifts of several distant galaxies and determines their recession velocities using the equation v equals hd. They use a value of h to be 68 km per second per megaparsec and estimate the distance of galaxy Z to be 1300 megaparsecs. Another researcher suggests that assuming the universe has been expanded at a constant rate, the inverse of the Hubble constant could be used to estimate the age of the universe. Using the data provided, calculate the recession velocity of galaxy Z. Give your answer in kilometers per second. Estimate the age of the universe by assuming the expansion rate given by Hubble's law has been constant. Give your answer in seconds and then convert it into years. Discuss why assuming a constant Hubble constant may lead to an accurate estimate of the age of the universe. Evaluate the usefulness of Hubble's law as a tool for understanding the expansion of the universe. In your answer, consider its strengths and its limitations. So pause the video now, and then unpause the video when you want to go through your answer. In our first one, v equals hd. H in this case has to be 68 from the question, so it's 88,400 km per second. We can then work out our Hubble constant into seconds by dividing by 3.09 times 10 to the 22, so it's 2.2 times 10 to the minus 18 seconds to the minus 1. Time is 1 over the Hubble constant, so it's 1 over that value, so it's 4.55 times 10 to 17 seconds. We can then convert that into years by saying there is 3.15 times 10 to 7 seconds in a year, so it's 14.4 billion years. Now, Hubble's constant is not truly constant. It changes over time. The early universe experienced faster expansion, especially during inflation. Later, dark energy has caused acceleration, altering the expansion rate again. So a fixed Hubble constant ignores complex dynamics, leading to an imperfect age estimate. Now, the strength is that the Hubble's law gives a direct, measurable relationship between redshift and distance. It was the first approximation for the universe's age and supports the idea of the expansion of the universe. Its limitation, though, it appears only reliable to distant galaxies, so local motion between galaxies can affect results. And Hubble's law alone cannot explain cosmic acceleration, or dark energy, or the early universe, so it's useful but not complete. An astrophysicist receives light from two distant galaxies. Galaxy A shows a redshift corresponding to a recession speed of 50,000 km per second, whilst Galaxy B, at a greater apparent distance, appears to be receding at 80,000 km per second. The two galaxies lie in near opposite directions in the sky. The observer notes, both galaxies are moving away from me, but I'm not at the centre of the universe, so what exactly is expanding? Later, the same observer questions the interpretation of redshift altogether. If redshift tells us galaxies are receding and the Hubble's law links speed and distance, why can't we simply reverse this process and see the beginning? Would this tell us where the universe started? Discuss what is meant by the observation that galaxies in opposite directions are both redshifted. What does this imply about the nature of the expansion of the universe? Critically examine the idea that redshift directly implies motion through space. In your answer, consider how redshift arises and whether recession velocity is the best way to interpret it. A student attempts to reverse the expansion by using Hubble's law to trace each galaxy's motion backwards to a single origin point. Evaluate the validity of this approach. In your answer, consider the assumptions involved in this extrapolation and the limits of applying Hubble's law over time. So, pause the video now, and then unpause the video when you want to go through your answer. In our first question, we can say that redshift in opposite directions shows isotropic expansion, that the expansion appears the same in all directions. So this suggests a homogeneous universe with our cosmological principle. So the observer is not special, expansion occurs everywhere in the universe. So all galaxies appear to recede from each other due to this expansion of space. Now, secondly, what we can say is that redshift can result from the Doppler effect, but also from the space stretching during photon travel. Now, cosmological redshift is better described by the expansion of space. Now, recession velocities from Hubble's law is a coordinate effect and not true motion through space, so interpreting redshift as motion is an oversimplification. More accurately, it reflects the changing geometry of our universe. Now, reversing Hubble's law assumes uniform expansion backward in time. This ignores the fact that the Hubble constant has changed over time. Our expansion is not constant. Now, general relativity shows there's no single centre. The Big Bang was not a point in space, but a state of all space itself. So tracing paths back does not give the location of an origin. The entire universe has expanded from one single point. A university outreach team hosts a public seminar on the origins of the universe. During the Q&A session, a guest asks, what makes scientists so confident that the Big Bang actually happened? The speaker gives two key pieces of evidence: the existence of the cosmic microwave background radiation and the observed relative abundance of hydrogen and helium in the universe. Later, a student reviewing the seminar is asked to explain why these observations support the Big Bang model and whether they rule out alternative theories. Describe what the cosmic microwave background radiation is and explain how it provides evidence for the Big Bang theory. Explain how the observed relative abundances of hydrogen and helium support the Big Bang model. Then evaluate whether these two pieces of evidence are sufficient to confirm the Big Bang model as the definite explanation for the origin of the universe. So pause the video now, then unpause the video when you want to go through your answer. In our first one, the CMBR is a uniform microwave radiation observed from all directions in space. It is the redshifted remnant of thermal radiation from a hot, dense early universe. It is near uniform and the blackbody spectrum at 2.7 Kelvin matches predictions from the Big Bang model. This supports the idea that the universe began in a hot, dense state and has expanded and cooled since then. The Big Bang theory predicts a specific ratio of hydrogen to helium due to nuclear fusion taking place in the early universe. Observations show 75% hydrogen and 25% helium by mass, consistent with these predictions. So this implies helium was produced before stars were formed, supporting the idea of an early hot phase in our universe. Now, the CMBR and the elemental abundance are strong independent lines of evidence for the Big Bang model. However, scientific models are always open to revision with new evidence. Alternative theories do not naturally explain the CMBR or early helium abundance. So while the evidence strongly supports the Big Bang theory, scientific certainty relies on an ongoing consistency with observations, not one single proof. Astronomers observe three distinct galaxies at different redshifts and collect the following data on their local elemental abundances and microwave background radiations using satellite instruments. A student is asked to analyse these findings and consider the implications for the Big Bang theory. Use the data to explain how observations for these galaxies are consistent with predictions made by the Big Bang model. Refer to both helium abundance and CMBR data. Evaluate whether the similarities and small variations in helium abundances across galaxies at different redshifts strengthen or weaken the case for a universal early nucleosynthesis event. Then suggest one reason other than observational error that might explain why the galaxy at the highest redshift shows a slightly lower helium abundance than expected. So pause the video now and then unpause the video when you want to go through your answer. The CMBR temperature increases with redshift, which matches predictions that the universe was hotter in the past. This supports the idea the universe has been expanding and cooling since a hot, dense origin. The helium mass fraction in all galaxies is close to 25%, consistent with predictions from the Big Bang nucleosynthesis. The data shows minimal variations despite redshift differences, supporting helium was formed right at the start of the universe. Therefore, both the temperature and helium data support the core predictions of the Big Bang model. The similarity in helium abundance suggests a common origin across space and time. This consistency supports the idea that helium was formed shortly after the Big Bang, not in stars later. The small variations are likely within the margin of observational or local environmental differences. Overall, the data strengthens the case for universal nucleosynthesis, supporting the Big Bang theory. The lower helium fraction could be due to stars reducing the proportion of primordial helium. High redshift galaxies may contain regions where star formation has already occurred, altering the original mix. Or variations in the density in the early universe could have led to slightly different helium yields in different regions. Astronomers analysed the elemental compositions of gas clouds in three separate star-forming regions within the Milky Way. These clouds were observed using spectral analysis to detect the abundances of several elements thought to be formed in the earlier generations of stars. A student reviewing the data is asked to consider what it reveals about the history of star formation in each region and how it relates to the current models of stellar evolution. Explain how the presence of elements such as carbon and iron in these gas clouds supports our understanding of nucleosynthesis in stars. Compare the data for the three regions and suggest which region has experienced the most generations of stellar evolution. Justify your answer using trends in elemental composition, and then evaluate the extent to which the small differences in hydrogen and helium abundance challenge or support the theory that most of these elements were produced in the early universe. So pause the video now, then unpause the video when you want to go through your answer. The carbon and iron are heavier elements not produced during the Big Bang. These elements are created in stellar cores via nuclear fusion. Their presence in gas clouds indicates materials recycled from previous generations of stars. This supports the model that where stars synthesize heavier elements and eject them into the interstellar medium upon death. Now, region C has the highest carbon and iron levels. These values suggest that the multiple generations of stars have formed and enriched the gas cloud. Region B has the lowest metal content, suggesting it's composed of relatively primordial material. Therefore, region C has likely experienced the most star formation cycles, while region B is the more chemically young. Hydrogen and helium only vary slightly across the regions, despite large differences in carbon and iron. This supports the idea that hydrogen and helium were formed in the early universe, with later stellar processes having minimal impact on their overall abundances. The consistency across regions strengthens the model of the Big Bang nucleosynthesis as the origin of most hydrogen and helium. While stellar processes produce helium, the small-scale variation suggests it only plays a minor role in altering the cosmic values of hydrogen and helium. Astronomers studying distant regions of the universe observe a very luminous object at the centre of a remote galaxy. The object emits electromagnetic radiation across a broad range of wavelengths, including strong radio waves and X-rays. The spectrum also shows large redshifts. This object is thought to be a quasar, an example of an active galactic nucleus. Explain what a quasar is and how it produces such high energy levels. The spectrum of the quasar shows redshifted hydrogen lines. One line observed in a laboratory has a wavelength of 486 nanometers. The same line from the quasars observed at a wavelength of 729 nanometers. Calculate the redshift of this quasar. Explain what the redshift you calculated suggests about the distance or motion of the quasar. So pause the video now, and then unpause the video when you want to go through your answer. A quasar is an extremely luminous and distant active galactic nucleus. It contains a supermassive black hole at its centre surrounded by an accretion disk. Gravitational energy from matter falling into the black hole is converted into radiation, producing huge amounts of energy. Z is equal to change in lambda over lambda, so it's 243 the change divided by 486 the standard, so it's 0.50. A redshift of 0.50 indicates the quasar is moving away from us at a high velocity, suggesting it's very distant and the universe is expanding. Astronomers aim to determine the distances to extremely distant galaxies. One proposed method involves using quasars as standard candles. Standard candles are astronomical objects whose absolute luminosity is known or can be reliably estimated. Explain what is meant by a standard candle and why they are useful in cosmology. A quasar has an estimated luminosity of 2.5 times 10 to the 40 watts. The observed intensity of the radiation from Earth is 2.2 times 10 to the minus 15 watts per meter squared. Calculate the distance to the quasar in megaparsecs. Give one reason why quasars might not be reliable standard candles. So pause the video now, and then unpause the video when you want to go through your answer. A standard candle is an object with a known absolute luminosity or magnitude. By comparing its absolute magnitude with its observed intensity, its apparent magnitude, the distance to the object can be calculated using the inverse square law. We know from the inverse square law that I is equal to the luminosity over 4 pi r squared. So r, or d, is equal to the square root of L over 4 pi I. So you pop in all the values and you get d to be equal to 3.37 times 10 to the 27 meters. We can convert that into megaparsecs, so it's 1.09 times 10 to the 5 megaparsecs. Now, quasars can vary in luminosity over time, or the luminosity can depend on the viewing angle, and is also not very standardized in what the value would be. Quasars were first discovered as intense sources of radio waves in the 1950s. Later it was found that these sources also emitted large amounts of optical radiation with very large redshifts, indicating that some of the most distant and energetic objects in the universe. Quasar 3C273 has an observed redshift of 0.158. Its optical luminosity is estimated at about 2 times 10 to the 39 watts. State what's unusual about the optical spectrum of the first quasars discovered and explain how this led to the understanding of their nature. Estimate the recessional velocity of the quasar. Assuming our Hubble's constant is 70 km per second per megaparsec, estimate the distance to 3C273 in megaparsecs. Suggest how the huge luminosity of a quasar such as 3C273 can be explained and describe the physical process responsible. So pause the video now and then unpause the video when you want to go through your answer. The spectral lines of the first quasars appeared unfamiliar because they were highly redshifted versions of known hydrogen lines. This showed the objects were extremely large distances, implying enormous intrinsic luminosity, and they were not stars but a new class of object. V is equal to ZC, so we know Z is 0.158, so its V is equal to be 4.74 times 10 to the 7 meters per second. We've got to convert that into kilometers per second, and then we can use that in the equation D equals V over H. H is 70, so it's 277 megaparsecs. Quasars are powered by the accretion of matter onto a supermassive black hole at the centre of a galaxy. As matter spirals into the black hole, gravitational potential energy is converted into thermal and electromagnetic radiation, producing the immense luminosity. In the 1960s, astronomers observed unusual objects emitting intensely in the radio wavelengths, which appeared as faint star-like optical sources when viewed through telescopes. Initially named quasi-stellar radio sources, these objects displayed extraordinarily optical redshifts far larger than those seen in typical galaxies. One specific quasar, labelled QX2, has an observed emission line at 668 nanometers, which is identified with a known hydrogen spectral line at normally 122 nanometers in laboratory conditions. Observations show that QX2 emits energy at a rate equivalent to 10 to the 13 times that luminosity of the Sun. A hypothesis proposed by astronomers is that the phenomena are associated with supermassive black holes located at the centre of distant galaxies, rapidly consuming surrounding matter. Explain, using the concept of redshift and cosmological distance, how astronomers determine quasars to be the most distant measurable objects in the universe. Using the data provided, calculate the redshift of the quasar QX2 and briefly explain the physical significance of your result. Discuss critically why the extremely high luminosity of quasars like QX2 present challenges for standard stellar models of energy generation and how these challenges support the hypothesis of accreting supermassive black holes. Evaluate the limitations and strength of using quasars as indicators of the early universe's structure and evolution. In your discussion, consider observational constraints, redshift interpretations, and assumptions in our understanding of quasar formation. So pause the video now, and then unpause the video when you want to go through your answer. The identification of quasars as highly redshifted objects implies they are seen at high velocities due to cosmological expansion. Large redshifts indicate extreme cosmological distances due to Hubble's law. High redshifts mean quasars emitted observed light in the early universe's history, placing them at great distances. Thus quasars are effectively cosmic beacons, visible despite extreme distances due to extraordinary luminosity. We know Z is equal to the change in lambda over lambda, which is going to be equal to 668 minus 122 over the lab standard 122, so it's 4.48. A very large Z indicates it's extremely distant, emitting observed photons when the universe was significantly younger. Now, quasars have luminosities vastly exceeding any known stellar processes. Standard stellar models such as fusions can't explain such enormous power outputs. Accretion onto the supermassive black hole can release gravitational potential energy efficiently, producing extreme luminosities. Thus, the accretion model around supermassive black holes is the most viable explanation, resolving challenges posed by stellar models. Now, the quasar's extreme brightness makes them detectable even at cosmological distances, allowing study of the early universe. Observationally, quasars may represent only the most luminous and active regions of the universe, potentially biased in interpretations. Redshift interpretations assume cosmological expansion is dominant, but local motion and gravitational effects could also complicate redshift analysis. Current theories of quasar formations depend heavily on modelling black hole accretion disks, where uncertainties still remain, so the conclusions drawn about our early universe may still be incomplete. Explain why it's difficult to detect exoplanets directly, especially those orbiting distant stars. Describe how the radial velocity method allows astronomers to detect the presence of an exoplanet. Explain how the transit method allows astronomers to determine the orbital period and estimate the size of an exoplanet using a light curve. So, pause the video now, and then unpause the video when you want to go through your answer. Exoplanets are much dimmer than their host stars and don't emit their own visible light. Light from the parent star overwhelms any light reflected or emitted by the planet. The angular separation between the star and the planet is extremely small, making resolution difficult without telescopes. An orbiting exoplanet exerts a gravitational pull on its host star, causing the star to wobble slightly. This wobble causes periodic changes in the star's velocity along the line of sight, leading to observable Doppler shifts in its spectral lines. A blue shift occurs when the star moves towards the observer, and a red shift occurs when it moves away. The pattern of shifts reveal the presence and orbital period of the exoplanet. The orbital period of an exoplanet is the time between repeated dips in the brightness on the light curve. The depth of the dip corresponds to the fraction of starlight blocked by the planet and can be used to estimate the planet's size. A larger planet blocks more light, resulting in a deeper dip. The duration of the dip also gives information about the orbital speed and distance from the star. A team of astronomers studying a distant star, TRX-59, suspects it has at least one orbiting exoplanet. The team uses both the radial velocity method and the transit method to investigate the system. The star is too distant and faint for any direct imaging of planets to be possible. Figure 1 shows the part of the light curve of TRX-59 obtained from continuous observations over several weeks. Explain why direct observation of exoplanets such as those around TRX-59 is difficult and outline the limitations this imposes on astronomers. Describe how the radial velocity method provides evidence for the presence of an orbiting planet around TRX-59 and explain what information it can reveal about the planet. Use the light curve in Figure 1 to estimate the orbital period of the exoplanet and suggest how the depth and duration of the dip could be used to estimate the planet's size and distance from the star. So pause the video now and then unpause the video when you want to go through your answer. Exoplanets emit little or no visible light and are vastly dimmer than their host stars. The brightness of the host star overwhelms any reflected light from the planet, especially at large distances. The small angular separation between stars and planets makes resolving them with telescopes extremely difficult, especially when the system is light years away. The exoplanet's gravity causes TRX-59 to wobble, producing a small oscillating motion in the star. This motion causes periodic Doppler shifts in the star's spectral lines, which can be observed as redshift and blue shift. The method can reveal the orbital period and the minimum estimate of the planet's mass, depending on the size of the velocity shifts. The orbital period is the time between dips. Here it is 5 days. The depth of the dip indicates how much light is blocked, which relates to the surface area of the planet. A deeper dip implies a larger planet as it blocks more starlight. The duration of the transit of 10 hours helps estimate how fast the planet is moving. Combined with the period, this gives information about the orbital radius, the distance from the star. An astronomical observatory is investigating distant stars for possible orbiting exoplanets. Below are the findings for a particular star CX8. A student argues that this data is sufficient to fully confirm the existence of an exoplanet orbiting star CX8. Using your understanding of radial velocity method, explain why direct imaging of the exoplanets is difficult. With reference to the transit data provided, sketch and clearly label a typical exoplanet transit light curve, indicating the 1.5% brightness dip. Explain how the shape of the curve can be used to estimate the size of the exoplanet relative to the host star. Using the provided radial velocity data, calculate the maximum fractional Doppler shift of visible spectral lines. Critically evaluate the student's argument that provided observational data alone is sufficient to confirm fully the existence of an exoplanet around star CX8. Consider the strengths and limitations of each detection method in your evaluation. So pause the video now and then unpause the video when you want to go through your answer. Direct imaging is difficult due to the extreme brightness contrast between exoplanets and their host stars. Planets emit very little visible light, overwhelmingly overshadowed by a star's brightness. Therefore, methods rely on indirect detection when they are more effective. Now, the correct horizontal axis should be time and the correct vertical axis should be brightness. Clearly indicate regular dips with periodic flat baselines otherwise. A correct indication of 1.5% dip in the brightness. The depth of the dip relates directly to the cross-sectional area of the planet relative to the star's area, and the wider or steeper the transit curve suggests the different orbital parameters or larger planets. We know change in lambda over lambda is v over c, so we can therefore work out change in lambda over lambda to be 1.67 times 10 to the minus 7. Now, consistent periodic Doppler shifts strongly indicate gravitational interaction with a companion object, possibly a planet. Transit data independently corroborates the presence of a body orbiting periodically, reinforcing evidence. Now, Doppler shifts will then be caused by other factors such as stellar activity or multiple orbiting objects. Now, the transit method alone could be confused by stellar phenomena like star spots or binary eclipsing systems. The combination of both methods strongly support exoplanets' existence, but further observations such as repeated transits are required to confirm conclusively. Quasars are some of the most distant objects observed in the universe. They appear extremely luminous despite their great distances. Many quasars show large redshifts in their spectral lines. One particular quasar shows a redshift of 2.1. The Hubble constant is 70 km per second per megaparsec. Explain how the redshift provides evidence for the expansion of the universe. Estimate the recession velocity of the quasar, and then estimate the distance to the quasar in megaparsecs. Explain how the existence and observation of distant quasars support the Big Bang model. Pause the video now and unpause the video when you want to go through your answer. So, in this question, how can we use this? So, the redshift of light from distant galaxies and quasars means the observed wavelength is longer than the emitted wavelength from the quasar. This suggests that they're moving away from us, support the idea itself that space is expanding. Now, we can work out our recession velocity of our quasar as v is equal to zc. We know z to be 2.1, we know c to be 3 times 10 to the 8, so we get 630,000 kilometers per second. We know d is equal to v over h, so 630,000 over the Hubble constant, which is 70, which is 9,000 megaparsecs. Now, quasars are only observed at very large distances as they have a high redshift, meaning that they only existed in the early universe. Now, this supports the hot Big Bang model, which predicts the universe had a hot, dense origin and has been evolving over time. An exoplanet is a planet orbiting a star outside our solar system. One of the methods used to detect exoplanets is the radial velocity method, which involves analysing the Doppler shift of spectral lines from the host star. The host star of a newly discovered exoplanet shows a periodic shift in its spectral lines. The hydrogen line that normally appears at wavelength of 656.3 nanometers oscillates between 656.1 nanometers and 656.5 nanometers. Explain how the observed periodic redshift and blueshift in the star spectrum can be used to provide evidence for the existence of an orbiting exoplanet. Calculate the maximum speed of the star along the line of sight. Then state one other method used to detect exoplanets and explain how it works. So pause the video now and then unpause the video when you want to go through your answer. Right, so a periodic redshift and blueshift of the star spectrum indicates the stars moving alternately towards and away from us. This suggests our star is wobbling due to the gravitational influence of an orbiting exoplanet. We know the change in lambda is 656.5 minus 656.1. We then divide it by 2, so that's 0.2 nanometers, as telling how much has changed from the equilibrium position. Then we can say v is equal to change in lambda times by c over lambda, so you can pop that through to be 9.14 times 10 to the 4 meters per second. The other method is the transit method, which detects dips in the brightness of a star when a planet passes in front of it. The amount and the timing of the dimming allows the planet's size and orbital period to be estimated. So this brings an end to our revision session today. If we've been successful and we've learned in our revision session, we should be able to answer A-Level Physics exam style questions, assess our understanding on A-Level Physics, and understand what topics we need to improve upon for A-Level Physics. So thank you so much for watching this revision session on AQA A-Level Physics Paper 3 in Astrophysics on the topic of cosmology. Thank you so much and have a lovely day.